Okay, good evening everybody. My name is Oliver Klein. I'm one of the solutions architect of Amazon Web Services. Thank you for coming everybody. It's a lot of people. My Chinese unfortunately is not very good, so I need to speak in English. I hope that's okay, but don't be shy if there are questions or anything. I want this to be very informal, so if you got a question, just let me know. We even got a whiteboard behind here, so we can talk through solutions. I really want this to be interactive. So today's topic is to look at how we can use some of the open source tools together with AWS to do some data analytics and to do that actually in real time. So for some of you, you might be very new to Amazon Web Services, so I'm going to give a little bit of an overview of what that is, how you can use it, how it works. We also going to have a live demo later, where we're going to try to look at a live Twitter stream and we start to visualize that. And I'm also going to give some information around URLs and code samples for you to look at. But like I said, if anything is unclear, just feel free to ask your questions. I'd love to answer those. So I wanted to kick it off today by quoting actually the CEO of our company, Amazon.com, Jeff Bezos, who said something which really drives the motivation of doing data analytics. And Amazon.com, as you might know, is a very data-driven company. So we measure a lot of things and we analyze them, and that allows us to improve customer experience. And where is that coming from? Well, basically, he said, we see our customers just like guests that we invite to a party. And we are the hosts, and it's our job as a company to do every day to make that aspect of the customer experience a little bit better. And you're all into data analytics, you work probably a lot with tools like R and so on. And you sometimes might think about, why am I doing this? And it really translates back into giving a great customer experience. How do you do that? Well, generally you want to start with collecting information and data before you get to the data analytics part. Where do you get that data from? Well, very often you already do collect a lot of data that you can start logging, like log files, etc. And from those you can derive an individual customer experience. If you have an online business, like Amazon.com, which is a retail business, you click through shopping carts and so on, that creates requests against the web service, creates a log file, and that eventually allows you to look at individual customer experience, what they did, what they've done, what have they put in their shopping cart, etc., and then improve that experience. And that is truly the motivation of data analytics. Increase or improve the customer experience, and as such, if you run a business, obviously increase your business revenue. Now, how do we get into open source? Where does that specifically fit into data and analytics? And you'll find that when we talk about big data or data analytics, a lot of tools like R are completely open source. There's some commercial versions of it available. But I think one important project that really kicked off the entire big data discussion is this yellow cute little elephant here, which is the logo of the Hadoop project. Hadoop was a framework that was created by two engineers at Yahoo, based on a research paper of Google. So that was an interesting scenario that was created here. But basically what Hadoop does, it's a system to do distributed computation and do that on a distributed storage, and do so on commodity hardware. And that was actually a deal changer to the world of data analytics. Because if we talk big data today, it's nothing new. Like, data mining has been done for the past decades, for many, many years. The only difference that we now have is that we do so on very large data sets. So having a possibility to actually do, standard basic data mining algorithms on large data sets required us to do that with different systems. And Hadoop was the first kind of project that kicked that off and said, you can use any kind of hardware, any kind of server you got lying around, can be commodity because it's a fault-tolerant distributed system. And the reason I'm mentioning Hadoop, because you probably see that today you don't do much pure Hadoop anymore. You very often do something along the lines of the Hadoop ecosystem, but it really kicked off an entire bunch of different projects that built on top of Hadoop and that allow to do some of your, or to accommodate some of the data analytics needs in a distributed manner. I mean, just to look at a few like Spark, Hive, Mahout, Flume, etc. Spark is a very interesting one. Obviously, there's also R on top of Hadoop. And I don't want to go to that list, but I just wanted to showcase on what different projects you can have and how that got really triggered from the Hadoop project. So if we talk about big data, just dissecting that a little bit further, what do we really mean by that? Well, people always say big data is the 3 V's, right? Volume and variety and velocity. So having more data coming in at a faster rate and having different kind of data sets. That is the status quo. And if I look at it from an engineer's perspective, I say, well, big data is still what we've done in the past, but there's one big difference, which is really we need to start to change and innovate on how we collect and store information and how we process it in terms of the sheer size and volume that we have. Because we can't do it on one single machine anymore. Previously, we loaded the CSV file into a laptop and we got insights out of that. So obviously, that changed. And to put that a bit into perspective, I just wanted to show an infographic. This is from gogolf.com. This is about 2 years old. So I reckon these numbers have, probably at least double. This is what happens in the internet every 60 seconds, right? And we see things which I find quite interesting. Obviously, lots of Google searches, like over nearly 700,000 Google search queries. An interesting one is 600 new video uploads to YouTube every 60 seconds. Another interesting one is 370,000 calls on Skype, 100 plus new LinkedIn accounts, 1,700 Firefox downloads every 60 seconds, and so on. Now, obviously not going into the individual pieces here, I just wanted to show what kind of data is generated at what kind of velocity every day, right? And if you build something these days, when you say, I collect a lot of data, tomorrow it's only going to be more, and the day after even more. So we need to think about ways of doing that a little bit more effectively. If you think about data analytics, you generally have some data generation somewhere, you collect it, you store it somewhere, you then want to perform the juicy part, right, to kind of do your computation, get an insight out of it, and then share that across. Now what you'll find, everybody in here has probably a smartphone in his pocket, a laptop on his lap, a tablet at home. Devices are cheap. Generating data is even cheaper. Everybody hogs on a 3G, 4G network, regardless where you are, and you continuously collect, generate data that we throw into a platform. So with that in mind, we have a very high throughput of data generation that comes cheaply, but the problem here still is there in terms of how do we collect and store that data, and how do we especially compute on that data that just gets bigger and bigger. And that is actually quite constrained. So here we still have the same constraints that we used to have. So how can we work with that, thinking about data just becomes bigger, yet we want to work on it with the same tool. So we need to change that a little bit. And we don't want to keep on racking and stacking servers just to kind of maintain a platform to analyze data. Now this is where cloud providers come in. So Amazon Web Services, for example, can help you to remove some of those constraints. So let me just dissect that a little bit. If we think about big data, we think about potentially massive amounts of data sets. If it's a cloud environment like AWS, you virtually have unlimited capacity in terms of storage. Now, there are different storage options. I'm going to go into it a bit in which one we want to use. We also want to, and if you work with R, you probably know that. You try something out, it doesn't work, then you try something else, and you put a model on it. You keep on trying things out. So experimentation is fairly important. If you think about an infrastructure, you also want to have an infrastructure that allows you to experiment. Even if you want to say, I want to simulate something, I want 100 nodes of a Hadoop cluster, for example, to run this R simulation on top of it, I want to have an on-demand infrastructure. And that also translates into, when are we doing data analytics? Potentially not all the time. Sometimes we just do it once a week. right? So sometimes we have this complete, a steady workload, and sometimes it just spikes up because we need to compute something. The cloud environment kind of gives you those capabilities. We feel very comfortable having this highly variable workloads. And the last one is more interesting because it actually defines what tools we're using and what storage we're using, which goes into, is our data structured? Think like a database table, that's structured data. Or is it unstructured? Is it like a data blob, an image, a CSV file, which is semi-structured data? And a cloud provider like AWS provides you with the tools to store all of those and process them individually. And it depends on what data we're processing or which service we're going to use. So today's talk is going to be about real-time data processing. However, I always like to refer to it as 3 different types of data analytics. The first one is obvious. The first one is create a report, a retrospective analysis of what happened in the past. Showcase me how my user used my game, how they used my platform, how they shopped on my e-commerce platform, for example, report it back. This has lots of value for me already because I understand my users a little bit better. I potentially identify problems, right? I potentially identify problems with my software, with my customer experience, etc. So lots of value in there. However, given the fact that we're always connected these days and our attention span is always shorter, I know that my mom always keeps on telling me that, like, you're way too nervous, like, you can't wait for something. I mean, yeah, because it doesn't work fast enough, right? And that's kind of the experience. Where 15 years ago, you would be happy to kind of do something, get a report in a week's time. Now I want it really fast, because if I don't get it fast enough, I potentially lose my customer. And I get a few examples of that. And then obviously in the direction also where R is used a lot is the other part, which is to now say, I know what happened in the past, I know what happens now in real time. Now I want to predict what potentially could happen in the future based on my past performance. So that's obviously the tie back. We can only predict if we're already doing this, right? If we don't know what happened in the past, then we can't create a good prediction model. So let's focus today a little bit about the here now, the real-time data processing and dashboarding of it. So the first question I would ask, how fast is real-time? Actually, we talk about real-time data analytics. And I just want to quote John Aykroyd. He's the CTO of Silicon Valley Data Science. He said something fairly interesting, and I totally agree with this. He said, there's no such thing as real-time. There's only near real-time. And typically, when we talk about real-time, what we actually mean is architectures that allow us to respond to the influx of data without persisting it to a database first. And this is an interesting statement, and it holds very true, because that brings me to the point of what do we mean with real-time? We mean to process data as it comes in, as it arrives into a certain stream storage, and then we process it in the present rather than in the future. Rather than saying we store it somewhere and then we process it later, we process it as it arrives. Now, if we say fast, people always ask me, what does that mean in terms of time, right? Depends on what you consider the present, and that depends on your use case. A good example is an e-commerce platform. How fast do I need to be? Are you going to click within 10 milliseconds on every different product? No, you won't. You click on something, you look at it, you click on the next item, you might put it in your shopping cart. So the attention span is generally a variety of seconds, 5, 10, all the way up to potentially 30, 60 seconds. So if we talk real time in an e-commerce scenarios, we talk about the attention span of a potential customer. If we say that's 5 seconds, 10 seconds, then that's what we define as real time. Take another example. I currently live in Hong Kong, lots of options traders there. Options trader, where we trade the market, seconds might not be fast enough. So here we go into the direction milliseconds. If we do arbitrage in the market, it becomes nanoseconds very often, to a point where some offices get relocated to get a faster connectivity to the stock exchange, for example. Think about a guided missile, right? A missile that flies around, potentially close to the speed of sound. or at least 1,000 kph, right, needs to make decisions fairly quickly. So if we talk about real time, the first thing that I would ask you to do is think about what is the real time that I expect. And you find more often than not, you're in the kind of second scenario, right, an attention span of a potential customer. So the solution to it is obviously a stream processing service or stream processing tool. By the way, an open source tool that does that also fairly well is called Kafka, which allows you to generate such a storage where you have the devices and the servers or whatever you might get your data from ingested into a stream, connect your applications to it, then immediately work on that data stream, do some simple validations, decision trees, etc., and then obviously still store it somewhere else into a database, into a storage server for later use. But now you want to work on that as it comes in. So let's try to understand that a little bit better and how Amazon can help here. What would we expect from such a real-time data stream? Well, we would expect a variety of things. We obviously would expect it to be highly available. Right? We have devices that are connected all the time. Our stream cannot go down. It needs to be there all the time. We want it to be fully scalable. Right now we have maybe one user. Tomorrow we get 1 million. The day after we get a few hundred again. So there's variability on what we expect on that stream. It needs to scale up and down. And we want it to be fault tolerant and obviously durable. Now, if you want to achieve this, how would you do it? Well, you would go out, build a lot of different data centers, build lots of autoscalable server infrastructure, build global load balancers, build global DNS resolution service. You get the picture. You would have to do a hell of a lot of effort to actually get such a stream storage that would really give you all those aspects. And this is where I want to dive into what is Amazon Web Services and why is it useful. Well, we provide you with infrastructure that is fully managed that can help you with that. So just click onto the next slide. Basically what Amazon Web Services, or AWS in short, does is we offer you web services in a variety of locations. So currently it's 11 regions across the world. So you can see that here on the map. So you got, for example, in the US, South America, in Asia, we've got Singapore, Tokyo. Our latest one, Frankfurt in Germany and Beijing in China. Now within those regions, we actually have a concept called availability zones. And this is fairly interesting because going back to the concept of building a stream that is highly available, if we would only have one data center here, then obviously that wouldn't be highly available, because if the data center is down, then all the stream would be unavailable. So what we do is we build individual clusters of data centers within those regions. And every region always has at least 2 or more of those availability zones. Now those clusters of data centers are connected to different power grids, different electricity grids, different network connectivity, different tier 1 transit providers. What we try to do is basically eliminate single point of failures. So if you run an application or service on us across multiple availability zones, you are highly available to a point where an entire data center could go down and your application remains available. So let's have a look at how that helps, and the services that I'm going to talk about today, a majority of them always span across multiple of those availability zones. In addition to that, for the data ingest, we also got edge locations. They're not on the map here, but they're 53 across the world, including one here in Taipei, for example. These are network entry points, great for your data ingest. So we have content delivery networks and DNS resolution services on those, but they're also great entry points for your initial data ingest. And that's important, especially if we think about collecting data from mobile devices. The last mile from here to the first entry point is the one where generally the connectivity is not as good. So it's important to get edge locations as close to the end user as possible. And we continuously expand, obviously, on that footprint. Now, when I say web services, what is it? So I talked just on that map around the little green bar here, which is our regional presences, different clusters of data centers that we built. But what do we stack on top of that? So obviously, we add a certain security level to that. So the security layer, which allows you, whatever you consume in AWS, you have full control over the access control of those services. You can monitor it. You have auditing capabilities, which can be very important in a regulated industry, and certain encryption functionality. On top of that, we stack what we call core services. So core services are things like compute, virtual servers, managed Docker infrastructure, managed application containers, for example, storage services, blob storage, or database services, networking services. So core components that you can use to build your project on top of us. On top of that, we stack what we call platform services. So those are higher level services, up the stack, I call them. So here we look at managed analytics services, managed stream storage, managed Hadoop clusters, etc. We look at services that allow you to completely deploy your applications out, or even have mobile services where you can directly talk from a mobile phone to it without managing any servers, effectively allowing you to build complete serverless infrastructures. And all the way on top, we also have applications like virtual desktop services, collaboration and sharing services, app delivery or email services. Now, today we're going to focus on this part here, the platform and the core services and how they can help you. Now, one important thing which I didn't address yet is the bar here on the right side. Every of these services that you consume within Amazon Web Services is, and as the name says, a web service. So it is an API. So whatever you do can be fully automated. And that's fairly relevant if we build an analytics platform that should scale, because we want to automate as much as possible. To make that easier, if you don't like RESTful APIs and you don't want to write the code yourself, we also provide you with software development kits, SDKs, in a variety of different languages, so like Java, .NET, PHP, Node.js, Objective-C, etc. So a bunch of software development kits that make it easier for you to kind of start using those services. All right, so let's try to build something now with AWS, and let's try to build a big data platform and see what we can do here. So I like to break it down when we talk about data analytics to say over a period of time we have data that comes in and we want to reduce that data to a point where we can get answers out of that data. To do that, we generally go through 4 different phases, which is ingesting the data, storing it, processing it, and then visualizing it. Now, this is not a one-way street. Sometimes you have iterations in here, and that's actually quite common. The reason I'm breaking this up is because it allows me to do this, which is to say, I want to look at the individual stage and which service could be useful to address that stage, and then we can go through it one by one. So on the ingest side, we get some cool open source tools, which are like log quotations or log collection tools, like Log4j. Flume is an interesting one. Fluentd is another interesting one. There are a bunch out there that I always recommend as a great place to get started to ingest data. If you build mobile apps, you might also be interested in using managed services for this. So we got a service called Amazon Mobile Analytics, which is part of our mobile SDK. So you can just include that in your app, collects information of how users are using your application, sends it back to you. Sometimes if you got massive amounts of data, especially in an enterprise setting, they sometimes tell me, well, I get this 500 terabytes of data. If I upload this, it's going to take me weeks to get it up into your cloud environment. In this scenario, AWS import-export is interesting. It's basically you send us your hard drives in and we load it up. So if you have massive amounts of data, other great way of ingesting it. When it comes to storage, and I'm going to go into more details on the individual services here, you generally have a few things. You have relational databases. Do not ever forget about those. A lot of people, they tell me, I'm no SQL, I don't care about relational databases anymore. I wouldn't do that, because sometimes when it comes to transactions, relational databases make sense, and they still belong into the big data mix. RDS is our fully managed relational database service. Then obviously the NoSQL databases is an interesting place to store data too. DynamoDB is our managed NoSQL database. Very often you want to look for certain object storage where you can just dump any kind of structured, unstructured data. That's what S3 would be like, our simple storage service. Search indices also belong into the mix of data analytics, and then obviously stream storage, which is what we like to use in real-time data analytics, which would be Amazon Kinesis. After we store that data, we kind of want to process it. Here again we have different options. So I talked about Hadoop earlier and the entire projects on top of Hadoop. So think things like Hive or Spark, Mahout or Spark R or R on Hadoop. If you want to use that, you probably want to leverage something like Amazon EMR, which is our managed Hadoop cluster. So with a click of a button, you get Spark or R running, for example, and bootstrapped into a cluster. A fully managed machine learning service. I'm going to go into more detail around that later, on how that can be used. Then data warehouses are also fairly relevant. When it comes to data analytics, often you still want to write a SQL query, because sometimes a SQL query is just a great way to kind of get some aggregation on data. If you want to aggregate data using SQL, you probably want to tap onto a data warehouse like Redshift, for example. Services like Data Pipeline can do your ETL process. If you're not familiar with ETL, stands for Extract, Transform, Load. It's basically just a fancy word of saying, take data here and put it somewhere else and transform it. That's what it means. And then compute services. So this is if you want to run your own compute, we got virtual service, which is EC2. And then we also got a newer service, and I'm going to demonstrate that one later, which is called Lambda, which is an event-driven compute service. And then after that, you can visualize your information. So here, I just showed open source tools here like Pento, Kibana, D3, but there are tons of tools out there. And as a matter of fact, one other thing that I wanted to point out is the AWS marketplace. This is fairly interesting when it comes to data analytics. Going back to the idea of it's experimental, you try something out. What if I could do that with software? I want to try Revolutionary. I want to try this new tool, right? AWS Marketplace allows you to do exactly this. So we work with software vendors together here, and with a click of a button, you can launch their software into our virtual service, and we charge you an hourly license fee, which is great. Because if you want to try out a piece of software, instead of procuring a license for a few $1,000s a year, you can now try it out and say, I try for 1 hour, play around with it. Maybe it's good for me, then I use it all the time, or I stop using it, and then it maybe cost me like a few cents just to try out the software. So we get lots of visualization tools like Tableau, Soft BI, MicroStrategy, in our marketplace, where you just say, I want to run JustMasoft, sorry, it has been renamed. It's TIBCO Spotfire is the new project. This is the newest one. TIBCO Spotfire, I want to run TIBCO Spotfire, click of a button, runs for you, you run it for an hour, you would pay only for that hour in terms of infrastructure, but also the software license. So that's fairly interesting if you want to play around with some tools. All right, so I'm just not going to go through everything, just want to address a few. And the first one, I'm quite fancying a log ingestion tool called FluentD. If you don't know about it, great tool, check it out. It's open source, so it's on GitHub, github.com/fluent/fluentd. And it's basically a data collector, which is very nice to use for log rotation. Very often you store a lot of log information or a lot of data somewhere, but you kind of want to move it to a central place. Now don't go and create cron jobs to do that, because I see that all the time. That's not very scalable and manageable way to do it. Use a tool like FluentD, for example. It actually gets integration into many different data sources where it can load from. So things like syslogs, application logs, even Twitter, for example, can be a data source. And then you can push it to another place. And here we have integration into our services. So for example, you can push straight into Amazon S3, our simple storage service, or straight into Amazon Kinesis, which is our real-time data processing stream. How would you do that? Well, FluentD does it all for you after you installed it. You just need to configure it. Here you see an example. This would be if I want to rotate my Apache 2 or Apache access log files here, and I want to push them into Amazon S3. It's as simple as just saying match S3 and put it in my S3 bucket, which I called my web logs. Now FluentD will automatically look at what new logs are coming in, and from Apache Access logs, push them out into your S3 bucket, where you can now pick it up from your data analytics platform. This is a great way if you have many different servers, for example, out there, and you just want to move log files somewhere. This tool can help you do that, and a bunch of other things, of course. Now, I mentioned integration also into Amazon Kinesis. What is Amazon Kinesis? I mentioned it's a real-time data processing stream. Let's dissect that a little bit further. It's a service that has managed distributed stream where you can throw in a payload of data, different events that are coming in, and then you can react upon those events in real time, right? As they come in, you can pick them up and do something with it. We manage the scalability aspect of it, so highly available, fully scalable, and we achieve that by also replicating your data across at least always 3 different facilities, data center facilities. So when it goes into a stream, it goes into at least 3 different data centers within the region of your choice though. So if you say I want to do that in Tokyo, it's not going to leave Tokyo. I wanted to give you an example because it's always a bit dry to just kind of say this is a service that's highly available and it does all that for you. Could that be used? Anybody knows Clash of Clans here? It's a little game, very popular. Yeah, it's from a Finnish game developer called Supercell, and it's about these little clans that run around. You can have your little villages and loot each other villages and build up your clan. They are fully powered on AWS, and they have been extremely popular. I think they've been #1 in the App Store in different countries for over 2 years now, which is crazy if you think about that. How do they achieve that? They're very heavy on the analytics side. They understand their user extremely well, and it allows them to kind of keep them on the platform. If you think about a game, the most important part is user retention. If your user stays on your game and keeps on playing it, that's where you drive the revenue out of it. User acquisition is obviously another interesting part, but if you retain the user that you already have, you don't need to invest so much into acquisition. That's exactly what Clash of Clans is doing. So what they do is, within the game, whatever you do, you select your characters, your clan, you move around, all the events that you do, they send them back into a Kinesis stream in AWS to process it in real time. But before they process it in real time, what they do, they plug a variety of applications behind it. The first application that they plug behind it is just store those information into an S3 bucket. To give you an idea, this is the amount of data that they collect every day. Just the in-game events create about 4 terabytes of data every single day, just on what people are doing within the app. Now, what they do with that data is they actually take that back into their data scientist team, and they try to find patterns to determine likelihood of user churn. So they found out that if you do certain things within the game, you're more likely to actually stop playing the game or continue playing the game. These can be simple things. Think about playtime. That's a simple one. But they found that even patterns within the behavior of your character can give them a relatively accurate prediction of he's very likely to stop playing the game within the next hour because he seems bored with it. And what they do is they use that information to use that model in their Kinesis stream, and for the influx of events, they continuously calculate the churn likelihood of that individual user. If he's likely to stop playing the game, to leave the platform, what they do is they send back a mobile push notification to the player to give him a free new goodie within the game. It's like a free new character, a free new sword, a free new item, for example. And what has happened? Well, if you play the game, you get bored and you go, oh, I got something free. Well, that's cool. I keep on playing. Right? And it works. It's impressive. I never thought it would have that much of impact, but Clash of Clans is a perfect example of if you use your analytics wisely, you can actually drive a lot of your revenue, especially when it comes to the gaming industry. So a good example of where real-time data processing is relevant. They would get that insight without a real-time data processing stream, but they can't react upon it. If you react upon it a week later and I send you an email, hey, I got a free new goodie for it and I already removed the game, I'm not gonna download it anymore. So it's important to react in real time. So how do we talk to Kinesis? Well, a bunch of ways. So remember, everything is a RESTful API, so we can obviously do an HTTP post if we want to talk to Kinesis. That's the simplest way. But to make it a little bit easier, we obviously got the software development kits. The open source tools that I mentioned, like Log4j, Flume, FluentD, all of those also have direct integration into Kinesis, so they just connect it to it and it sends its event to Kinesis. Also for Taiwan here, an interesting thing is you got lots of chipset manufacturers, and right now one of the newest trends is what is referred to Internet of Things, IoT. MediaTek is pretty big in that, for example. Kinesis is a great way, if you produce IoT devices, to also stream in information. So we also got a specific Kinesis producer library for IoT devices, and that is written in the wonderful programming language of C, without the pluses. So, because we talk IoT. But we get a bunch of different SDKs, so if you go into that space, quite interesting. After you put it in the stream, this is where the real-time data processing stream is interesting, because you could argue, I could just create a queue. If I have a queuing system, then I can do all that. Not really, because what you can't do in a queue is to have multiple applications working on the same queue without duplicating that data. A real-time data processing stream can do that for you. So you can say, I plug, for example, 4 different applications behind it. One application does nothing else but to store it somewhere else for later use. Maybe do some simple aggregation, push it in a storage place, like an S3 bucket. Another one could be just look at what happened over the past 1 minute, put it in a dashboard. This could be a NoSQL database, like DynamoDB, to kind of visualize what's going on. Another one would be a decision-making tree. This is what Clash of Clans does, decision-making tree, or any kind of pre-computed model that you use to kind of get a hold of it and make a decision. And obviously feed your machine learning algorithm with it. Now, important to know is those can all work independently on the same amount of data that comes in. This stream here keeps the data stored securely for 24 hours. So even if your application drags a little bit behind, is a little bit slow, you can pick up again from where it is. And all of them work independently on their own data horizon, on where they are, the position, basically, in that stream. So that's great. We can put multiple applications behind it. By the way, I want to point you to what we call AWS Labs. So we got a bunch of teams that work on some open source connectors and tools specifically to use with AWS, such as Kinesis. We got a bunch of connectors there. All of those are licensed under Apache License 2.0, so fully free to use for you in any commercial, non-commercial settings. You can contribute to it, you can commit to it, change, modify, whatever you want to do. Check out AWS Labs, fairly interesting if you're a developer. All the tools and services, we get integrations to it. All right, one interesting way of using Kinesis is to tap onto another open source project called Spark. Anybody familiar with Spark? Not so popular here, we get heavy R users. Okay. There's an R extension for Spark called Spark R now. Which is fairly interesting. Why do I bring up Spark? Because if we talk about big data, we talked about something like Hadoop, and how Hadoop can build a cluster for us, and we don't need to worry about scale, right? We can just have thousands of nodes potentially within that cluster. You will find that Hadoop doesn't perform so fast though. Why? Because when it does what they call MapReduce phases in between, it has a shuffle phase where it needs to write things onto the hard drive. So that slows down the entire process a little bit. So one team from UC Berkeley wrote a paper around how you could build something just like Hadoop, but do it in memory. And the result of that was then Spark, which is basically an in-memory analytics cluster. How does it do that? It leverages on something called RDD, which stands for Resilient Distributed Data Sets. So it's basically just a way of having data stored resiliently across multiple machines within their memory, and be aware of things like data locality and so on to further optimize it. Bottom line is, if you compare Spark operations to pure traditional Hadoop MapReduce, you'll find it's about 100 times faster, which is pretty impressive. This can be used together with some libraries. So Spark itself just gives you Java Scala language to kind of operate on your data sets. It also has interesting projects like the MLDM, which is basically the pilot kind of integration into Spark. It also has integration into R. This is still early days, but I think it's going to be fairly interesting in the future. So if you want to say I want to run an R program across a big cluster of Spark to optimize it, that's an interesting way. And it also has something called Spark Streaming, which can be used to work on real-time data processing streams, and that has a direct integration into Amazon Kinesis. So let's say if I would, for example, I'm going to demonstrate that later, I'm going to use Kinesis and I'm going to feed it with a Twitter stream, for example. If I want to say, find me all the tweets, with a certain text, let's say open source, for example, and count me those over the past 5 seconds, something like Spark Streaming can work on those windows and do so in a cluster. So even if that stream would be massive, it can just scale out, do it fairly fast. Now a count operation is fairly simple, but there are more complex aggregation methods that you can call with Spark too. Now, when we process data, I wanted to highlight one other Amazon Web Service which is fairly interesting. It's one of our newer edition which we launched last year during our reInvent conference. AWS Lambda is basically a way of running your code in the cloud, fully managed, based on events that are coming in, and you don't need to worry about any service. So you just put in your code and you can run your code. Now, when I say that, you're going to say, well, that just sounds to me like an application container. Well, it can be used that way. You can just put your code and invoke it. But the more interesting part is this code can also be triggered through event changes or state transitions within your AWS environment. So you have, for example, things like S3, where you can put files in, or DynamoDB, which is a NoSQL database. You can react upon new items. So if you put a new file into your S3 bucket, an Amazon Lambda function is automatically triggered and runs your code on it. If somebody writes a new item into your NoSQL database, a new item inside triggers a Lambda function, does something with it. It also integrates into Amazon Kinesis. So whenever there are new events in the Kinesis stream, it triggers a Lambda function with your own code to work on that event. And you wouldn't need to worry about availability or scale. So we fully manage this across multiple availability zones, and we scale it up to match any kind of event throughput rate that you have. Right? If you want to throw 1 million events per second in there, it's going to get executed 1 million times through Lambda. The good news for you, because then you're going to ask me, well, isn't that expensive? No, because it's actually much cheaper than a lot of our other compute services, in the sense that we only charge you for execution time. So you can put your code, if it's not getting executed, it costs you 0, nothing. We only charge you for the actual execution time. You run the code, how long did the CPU process it? That's the execution time, and we charge you only for every 100 millisecond of that compute execution time, which is fairly interesting. Available right now for Java 8 and JavaScript, so all your Node.js stuff would work on this, and we're also looking into having further other programming languages that we can leverage with Lambda. This is fairly interesting to connect with some of our services. What are some of the things that we could do with it? I would use Lambda to clean and massage my incoming data. If I do log rotations and I put log files into an S3 bucket, then you can create a trigger. Every time a new log file is in my S3 bucket, call that Lambda function. The Lambda function could open the log file, maybe it's a zipped log file, unzip it, do some single aggregation, push it somewhere else, massage it, remove things that you don't want to have. A great way to kind of also say, I want to load things into my data warehouse periodically as they appear. Lambda could be used for that. Every time we dump a new log file into an S3 bucket, Lambda function loads it up, puts it into your data warehouse. Redshift is one example. You can obviously put it in any system you want. You can write your own code. And the more interesting part is, together when we talk about real-time, together with Kinesis, every time there's a new event that comes in, that code is executed so we can work on that event. And we're going to try that later with a demo to kind of find hashtags on the Twitter stream. And since this is an R meetup, you can also run R in AWS Lambda. And I normally don't show this, but I figured it would be fun to do that here. There's a cool blog post that demonstrates how you can use JavaScript to run R. Because basically what Lambda does, it is a container. And within that container, you have all the normal Linux libraries available. So you can actually run R through it, because R is part of it. So what you can do is you could write and just say, very simple R function here, where I say I plot something out, for example. I call it say hello. You could store this as your test1.r file, for example, and then your Lambda function could look something like this, where you just say execute that file. If it was successful, do something else. Now, let's think this through. This is obviously just, it looks like just a proof of concept, but this could actually be used in an interesting environment. Thinking about the idea of rotating your log files into an S3 bucket, right? This could trigger a Lambda function, picks up that log file, and then, for example, creates a report with R, plots the information out of that log file, puts the output back into my S3 bucket, right? So that it's now a PNG file that I have readily available for me to look at, for example. And then that's fully event-driven. So no cron jobs, no scheduling, no servers. It's just fully event-driven, and you only pay for the execution time of it. So even if you say, I don't write JavaScript or Java, might have a look at Lambda. Can be quite useful. This is the URL if you're interested, with a complete walkthrough on how to actually run R, a little R function off within Lambda. Now, obviously, this is not useful if you want to run a very complex R statistical function on it, right? That would run for a few hours or something like that. This is meant to do a quick interaction, work on something in an event-driven fashion. So just keep that in mind. Now, just moving on, just wanted to highlight another concept of NoSQL databases. So we have a service called Amazon DynamoDB, which is basically our fully managed NoSQL database. Now, before I dive into what it does, I just wanted to highlight what NoSQL databases do and the importance of it. So, first of all, Amazon DynamoDB is actually based on a paper that some of our engineers at Amazon have written many years back, which they called Dynamo. And that was kind of the first of its kind NoSQL concept. NoSQL meaning that you have a database that can handle structured, unstructured data. Sorry, unstructured data in the sense there's no schema in the database itself, but it allows to fully horizontally scale. This paper was written even before AWS existed. And the reason we've done that is because we have a retail business, right? Amazon.com, which is very popular, especially in the Western world, a little bit less here for now. What you have there is a shopping cart. And if you think about an e-commerce experience, people click through the website and they put lots of things into the shopping cart, out of the shopping cart, they have sessions running. So it's a very write-heavy application on the database. Now, if anybody of you ever managed a relational database, you know how painful it is. If you get lots of writes, that doesn't scale fairly well. All your weak replicas and slave, they don't matter because you need a master to write to the database. So the concept of Dynamo, and which eventually led to the idea of NoSQL databases, was to say we built a database that doesn't need to have this transactional consistency, but allows us to have multiple master databases. That's what a NoSQL database allows you to do. Have a partitioning and sharding key that automatically writes to multiple master nodes and fully scale that database out. Now, if you ever ran your own NoSQL database, your own Cassandra cluster, your own MongoDB, you probably know how painful it still is to kind of still maintain that. And this is where DynamoDB becomes interesting, because it takes away that pain for you. So this becomes a NoSQL database service. So you create a table and you don't worry about anything underneath. You don't worry about which server, how that's replicated, or availability. We don't put any limits on it, so it has complete seamless scalability in terms of storage. You put in as many data as you want, and you can read and write from that database as fast as you want. So you just tell us how much throughput you want to have. You want to say, maybe I just want 1 write per second. And a minute later, you decide, I want 1,000 writes per second. And then a minute later, again, you decide, maybe I just need 100 writes per second. You can do that with Amazon DynamoDB. You can adjust the throughput all the time. And how do we charge you? Based on that throughput. So if you say, I want to have more throughput, we charge you for more. If you turn it down again, and that's interesting, obviously we charge you less than that. Another element is we use SSD hard drives on the underlying storage layer here, which allows us to give you low latency performance. So on queries, you see a single-digit millisecond latency, so between 0 to 9 milliseconds on queries, which is fairly interesting. Question there, Matt? Very good question. Yeah. So the question was if we could automatically adjust the throughput capacity based on timing or potentially load in DynamoDB. So fairly good question. The answer is yes. There's actually an open source project that helps you doing that. Because DynamoDB is an API, so it's a web service, so you can easily adjust that throughput at any point in time. And there's a project called Dynamic DynamoDB, which measures the throughput. If you get to a point where you reach threshold, it automatically increases your throughput, and vice versa. If your load goes down, and it looks at CloudWatch to do that. CloudWatch is our monitoring service. The load goes down, it turns down the throughput and effectively makes you save cost. There's another one, I think it's called Auto Scaling DynamoDB or something like that. The best one I've seen is Dynamic DynamoDB, and a lot of our customers are using it actually for their production environment to automatically have it readjusted. And it's a very good point, because even though you can adjust it, unless you would scale it down, you don't save as much cost as you could. I'll give you my email later, I can send you the URL. Now, just looking a little bit further at what we could do, one last thing I just wanted to mention it. One important thing when it comes to a database is durability. You don't want to lose data, right? How do we do that? Replication. DynamoDB does that for you, so whatever you write inside here is automatically replicated across 3 facilities, 3 different data centers, before the write is acknowledged. So there's a quorum acknowledgement, meaning if it says you've written to DynamoDB, it already has been replicated across these other facilities. So even though if now an entire facility would burn down and go up in fire, you would still have your data available. So that's another interesting element here, that you don't need to worry about that. It becomes a table, and I write to it, and that's it. I just want to give you an example for this. Shazam, I'm not sure if that's so popular. It's an Israel-based startup. Anybody knows Shazam here? Few? That's all right. All right, it's a mobile application which allows you to kind of, if you hear a song in a bar somewhere, or a concert or whatever, you tap a button, it listens to the sound, it fingerprints the music, and it will then tell you the name of the song that somebody's playing. So I sometimes DJ in my free time on the weekends, and that's how I build up my playlist. I go everywhere to bars, and this is cool, and then I build up the tracks. All right, now you know my secret. But Shazam, just to give you an idea, they are a heavy user of DynamoDB to store the fingerprints of the songs. And it has become a really popular app. It generates about 500,000 writes every second onto the DynamoDB table when people start fingerprinting music, which is impressive. 500,000 writes every single second against DynamoDB. So for them, using something that is managed, where they don't need to worry about service, was fairly interesting. Another interesting element is Super Bowl is a big event, a baseball event in the US. And during Super Bowl, a lot of people are apparently using Shazam to kind of listen to what music, understand which music is currently being played. Shazam is using their own fingerprinting algorithm, and for that they use virtual servers on our platform. During the Super Bowl, they need 200 additional servers just to power that fingerprinting service and virtual servers. Now, also to your question, when it comes to scaling things up and down, the same goes for servers, right? So that's a great thing, because the Super Bowl, after it's done, you just shut down all your servers. Think about the element of cloud computing, and don't just see it as a cheap place to get virtual servers. When it comes to data analytics, think about how can you make a yellow little elephant happy. You give him lots of nodes, right? You give him lots of servers so he can work in a distributed manner. Now, as a matter of fact, we charge per hour, right? So one instance for 100 hours is the same price than 100 instance for 1 hour. And if you think about a distributed model like Hadoop, it actually has fairly linear scalability in its performance. It's slightly sublinear, meaning that you get the same job done faster for the same price. If your current job needs 100 hours to complete and you only do it on one server, well, you could do it on 100 servers, same price, but do it within an hour. That's pretty powerful. And just one last thing here, it's not on the slides, but we get another interesting pricing model called spot pricing, which allows you to tell us how much you want to pay for a server. So even though we say this server costs 70 cents an hour, for example, you can say, I want to pay 1 cent for it. And we continuously have a market rate, which is based on supply and demand of the service. And that market rate, you find very often it's about 90% cheaper than the on-demand price. Now, if you set a bid price like this, and the actual market rate is below your bid price, you get that server for not only the price that you're bidding, but the actual market price that you have. So one really cool thing that you can do is you set a bid price on the on-demand price, and you get the actual market rate much cheaper. If you translate this into this, you could say, I need to complete my job within 100 hours, but I could do it faster, so I could just do this. But in addition to that, I could take the other 99 instances in the spot model, which maybe just cost me a few cents now, so I get it done faster and even cheaper. And you'll find that our fully managed Hadoop service actually has integration into the spot pricing model, so that you can tap onto the actual market rate of service, which is much, much lower than the on-demand price. And if that's something interesting in, just contact me. I can explain it a little bit further on how you can do that. Pretty cool. I mentioned data warehouses earlier. Again, I still think SQL is a fairly important language, and even if you write your R programs, sometimes to just do a simple aggregation of the data before you load it in, fairly often you do it with SQL queries. Now you'll find that these SQL queries often aggregate data across columns. So what you find in a relational database like a MySQL or PostgreSQL is that all the information is stored in a row. If you would look on the disk drive, actually that row always sits next to each other. So if you now throw a query against a relational database where you say select, count of this column where field is like this, it needs to load up all that data, then remove all the columns it doesn't need, and then aggregate them, which is not fairly fast. This is where columnar storage can be used, and most data warehouses actually use columnar storage. So instead of storing rows, it's storing it in columns, and that makes it much faster for you to do aggregation queries. So great for analytics use cases. This is exactly what Amazon Redshift is doing too. It's a fully managed data warehouse of columnar storage. This fully scalable, our current upper limit would be 1.6 petabyte, right? 1.6 petabytes. So that's 1.6 times 1,024 terabytes. That's a lot of data that you can store in that data warehouse. And we manage a fully scalable cluster of data warehouse nodes. For you, the more important part is it has full ANSI SQL compatibility by using ODBC or JDBC connectors, so you can write your SQL queries just the way you used to do it. With all the tools, if you have business intelligence tools, you can connect them to it. They can also load up data straight from DynamoDB and S3. So again, going back to that use case earlier, store your log files in S3, then move them up to your data warehouse. Here you can now throw a query against it with SQL. In terms of cost, you'll find that comparing this to other commercial products, it's about a tenth of the cost of what you see out there in the market. Fairly cost effective. And one of our biggest customers of Amazon Redshift is Amazon. And this is funny because you might think that's obvious, but we actually need to win the business of Amazon.com. We're different divisions of Amazon, and our retail business says, well, why should I use Amazon Web Services? Well, and then we need to make a case for it. And as a matter of fact, Amazon.com is using Redshift for their web log analysis. So the online retail business is doing that. What are they trying to do? They go through all their logs. Remember what Jeff Bezos says earlier? Customer experience is important. They tried to understand the customer behavior based on the click-throughs that they had on the log files. So things like who's browsing the website but not buying anything. Which products are the winners? Which products are fairly often looked at? Which products are clicked at? What is the sequence that somebody had to go through products that actually led to a higher conversion rate? This is interesting. And you probably experienced this yourself when you did some e-commerce online shopping. Unless you have a very specific idea of what you want to buy, you start with the first product, then you look at it and you're like, okay, this is interesting. And then you go to the next product which is related to it, then you start comparing it, then you go back, then you look at another product before you make your final buying decision. And that is very often around price, around functionality, etc. Understanding how those sequences lead to each other can help you improve the upsells or the possible recommendations that you give your users to further increase that conversion rate. So simple log files can help you do that. And again, just to give you a few metrics here, Amazon.com just web logs generate about 2 terabytes of new data every single day. And the largest table in the data warehouse right now is about 400 terabytes large. Just one table, 400 terabytes. So with the queries, you'll find that we scan with Redshift about 2.25 trillion rows of that data in about 14 minutes, and we load about 5 billion rows of data, full table scans, within 10 minutes. Just to give you an idea of comparison, these are actual numbers from our online retail business. So they used to have a Hadoop platform to do this log transformation with Pig. Took them for the same amount of data about 2 days and 1 hour. And they then switched it to an Oracle database before actually running it with Redshift. The Oracle database, they had about 90 hours up to 8 hours depending on the complexity of the queries, compared to now 14 minutes. So that's the kind of improvement that you can see in terms of performance. Juicy, Amazon Machine Learning, was released last year at our San Francisco conference. So let's have a look at it. Amazon Machine Learning is actually a service that is fully managed for certain machine learning algorithms, and those are powered or based on Amazon's internal system, so the retail business. So we have certain algorithms that we developed, and you can tap onto those using Amazon's machine learning service. What does machine learning mean? It means you create a model, you train it, you evaluate it, and then you get predictions out of it. That's what this service does for you. Where is it getting the data from? From different data sources. You can get it from S3, you can get it from your relational database, from MySQL, for example, and obviously the data warehouse, Redshift, S3, RDS, and Redshift. This is where we get the data from. We can then create a model, and then we can request predictions, both in batch, right? So give me predictions for those hundreds, thousands different users, or in real time. This is the current user, give me a prediction for it. So let's look at that a little bit further. 3 steps with Amazon Machine Learning, just like with any machine learning. Basically, train your model, evaluate it, and retrieve the prediction. So let's look at the train model first. This means that we're going to create a data source where we're taking the data from for which we want to train the model, and we want to explore it, understand it a little bit better, maybe clean it a little bit further before we train the model, and then effectively train the model. All right, let's go to this step by step. These are actual screenshots from my console apologize, you might not see that very well from behind there. So I'm just going to talk you through. So the first thing is creating a data source. So this is where you define your location of input data. So this could be your data warehouse, your log files in an S3 bucket. You put that in here, and then you say load it up. What Amazon Machine Learning now does, it loads up that CSV file, for example, and it tries to find the different data types that are in there. So here's an example where we see age, and campaign code, and contact, and it found that age was numeric, for example, between, well, this is an old data set, 50 and 57. And it gives you certain sample values here of what it found in that data source. So this is just an initial go-through. This allows you to define the data type. So age is a good example. Age can be numeric in the sense from 0 to, you know, as old as it gets, I guess. Or it could be a class, right, where you say from 0 to 18, from 18 to 25, 25 to 35, and so on. This is the place where you can modify the data type and say, what is it actually that I loaded in? We, by default, try to determine that, of course. And then the important part is the target variable. So what our machine learning service does for you, it can give you a prediction against the target variable. Think about a classification algorithm, for example. Think about, is he going to buy this or is he not going to buy this? A yes or no answer. That could be a target variable. So as you know, when we train a model, we obviously need to know the outcome so that we can train it. And then later, the outcome is we want to have predicted. So here we then select that target variable where we say our data set with which we train, here we have the target variable and we know the answer. And this is what later you should predict after creating the model. Then we review it, and that's it. Now we create the data source object. Everything is an API, so we can also do that programmatically. Since I talked to a bunch of data scientists here, this is Python code. So it is available in both Retrieve for yes, it should be. It should be. This is the latest Bodo version where it runs on. So I think that should be Bodo 3. Give you the details later to make sure that it's in there. It should be in there for sure. Unless you use a very outdated Bodo library, which Bodo 3 isn't. It's one of our newest. So yes, should be available there. And this is the way it would look like. So that initial creating data source would be loading up Bodo library and then creating the data source. Here we just loaded up from an S3 bucket. This is just a sample. All of this has been done also to the console. It's just to show you, sometimes it's nicer to just do it all in like 3 lines of code. Now, after we created the data source, what Amazon Machine Learning also helps you to do is to explore and understand your data. So it loads it up in, and then it gives you certain, distributions, for example, and plots it out for you so you can explore the data. And that doesn't look very fancy, but I want to point out one thing here which is fairly interesting, which is something I always talk about. When we want to build a good model, we want it to be not noisy. We want it to be good input data. So what does that very often translate to? To a good correlation from the input data property to the target variable that we want to predict. So if you load it in, Amazon Machine Learning does that, exactly that for you. So this column here is super important if you don't know if you should or should not keep a certain property when creating your model, because it gives you a correlation to the target variable. So obviously the more correlation there is, the better that property can help us create a good model. If we have a variable that has a very low correlation here, we probably should remove it. Right? We should consider removing it because it's noisy. A very simple example that I always give here is if you want to predict a certain thing about your user, like you want to find out is he a hardcore gamer, is he an occasional player, etc. And you have all kinds of information from that user, like his email address, his phone number, his transactions, his game sessions, etc. If you measure correlations to target from something like an email or phone number, do you think it's going to be good? No. there will be very low correlation. Your phone number doesn't tell you what kind of gamer you are. Very unlikely, right? Unless you have a very specific one, like 888888 or something like that. Then maybe a very lucky gamer. But you find that properties like this, you want to measure correlations first to decide if you want to keep them inside or not. So even though this is just in one slide, some people overlook this. I think this correlations to target is fairly useful for you to get initial hold of your data and remove what you don't want to have. It obviously visualizes also categorical attributes. You can dig into some sample records and say, give me some sample records to further kind of evaluate it, give you distribution of numerical values, etc. So for example, here age, we see that's an interesting curve where most people are in 30 years old here. This was actual data coming from a bank accounting system. Now, after we create a data source and we explore it and we now decided on what attributes we want to keep or not, we obviously want to start training the model. So how does that work? Well, we select our input data. This is the data source that we created, so we just select it. Oops. And then based on the target variable, Amazon Machine Learning will now give me a model type. So if my target variable was a numerical value, it will determine that's a linear regression algorithm that should be used here. You can further fine-tune that if you want to do it. In this scenario, just said that's fine with me, so I'm going to start training that model. What it will do by default is it will take 70% of the data source that you included to train the model, and it will take 30%, cut it out, for further evaluation, which is our next step. And obviously, this can be done through Python code with the Boto library, of course. So here we just say we want a linear regression model being built on that data source that we imported. Now, the next step is, after we train the model, so now Amazon Machine Learning churns and it creates a model for you, we now want to evaluate if that model is good before we actually throw predictions against it, and potentially optimize it if it's not good yet. So this is the second step. So we explore the model quality. So depending on the model that you choose, it will look like this, which is an area under the curve that tells us how many false negatives and positives we have. Whoops, that was too quickly. Or here we have a numerical prediction target, a multi-class classification. So you can see kind of like, where's my distribution, how is it performing, how many errors do we have? And it also translates that to you into one average AV1 and baseline score. And that score obviously tells you how good that model performs. This is a value between 0 and 1. If it's 0.5 or below, it's for binary classification, that would be as good as random guessing. So that's not what we want to have. So we want to have something generally between 0.665 all the way up to 0.99192. If it's above 0.9 something, if it would be 1, then you have an overfitted model. So that's not good either. So you want to have a score roughly there. We highlight that with you by colorizing it. So it would be bad, it would be red. Here it's a good model, and we say, well, it's a better baseline. Sometimes we say it's a very good baseline, etc. So it gives you an idea of how it's performing. How do we evaluate that? 30% of your training data was used to evaluate this. You can also fine-tune those models. So here I used, this was a binary classification. So it will give me this area under the curve. And now I can move around this needle to kind of play around if I want to have more false negatives or more false positives by basically cutting off my threshold a little bit earlier. So it would look something like this, and swipe that around and find what you feel more comfortable with. I think the false negatives and false positive element is fairly important here, because for some of the stuff, the false negative might just be okay. Sometimes that's a really big issue and you rather prefer false positives, for example. So it allows you to quickly adjust that and fine-tune it. Now after that, we now train the model, we evaluate it, we say it's good, let's throw predictions at it. So how do we do that? Batch predictions is the first one, is to say, okay, I have a large amount of volume of data that I want to have predicted. How would I use that in a business scenario? Well, I want to send out a marketing campaign to my customers. But before I do that, I want to know, who are the customers of my database that I should target, for example. That's a good example. Here I dump down a data source of all the data that I want to have predicted, and then I can request that through the Service Console or also the API, of course. So Service Console would be create new batch prediction, click. Here's my CSV file or my input file, whatever it is, and it will throw predictions at me, or via an API. Here's Python code again, so I could just request a prediction like this, and the outcome will then be an output file that would be put into your S3 bucket. So here we did a binary classification, which would basically give me yes or no, so 0 or 1, and then it also tells me the score, which gives me the amount of accuracy that we have, so how accurate we've done that prediction. So if we get a good score, obviously then that's something that we want to keep. The same thing can be done in real time. So this is great if you want to immediately react upon what people are doing. So something within your website, for example, if you want to straight away get a prediction of what your users are using within your website, then you can do that again through the API or also the SDKs that we offer. How would it look like? Something like this. For example, this is Python code where we say, use this model and predict it with what? Well, here's the input. I just put key value pairs here. Obviously, this would be the information that you gave the model earlier when you created it. You know, like his profile, his transaction, where he currently clicked at, etc. That's what you throw in. And then the API will immediately return to you the prediction that it calculated in a JSON format. So you can even do it straight from your website, for example, through JavaScript, and then get the prediction back. Here we have a linear regression algorithm that we used where the predicted value would be numerical, and it would give me back that predicted value straight away. So this is a great way if we want to get real-time predictions through it. Now, in terms of machine learning algorithms, you probably know all of this, but I just want to run through it. These are some of the more common kind of algorithms that we see. Classification, things like put things in a bucket. I have a predefined bucket, like a gender, like an age ratio, like a yes or no question. That's a classification. A good example of that is sentiment analysis, like something that became very popular on social media. Is that person tweeting something good or bad about me or something neutral? That's a classification problem, right? Saying I have good, bad, and neutral as classes, find ways of determining what puts in where. Another algorithm is linear regression, so predict a trend, right? Things like what's my sales revenue for next month, for example. A good other example of that is, I always say, if you ever used Excel sheets and you created a graph and you right-click and say create trend line, that's a linear regression right there, all right? Now, those are the two algorithms that are currently supported in the Amazon Machine Learning Service. We're looking into including other machine learning algorithms further into it too, also relying on your feedback here. The reason we chose those is because it's obviously fairly easy algorithms to say what is my target variable. Now, sometimes we also look at clustering algorithms. So if you think about something like Amazon.com, other people bought this, like a recommendation, that fairly often translates into a clustering algorithm, something like a k-means, a k-nearest neighbor. If you want to do that, you obviously got R and also other open source libraries like Spark MLlib and Mahout. All can be run fully managed in Amazon EMR. So that's a great place to get started if you want to say, I want to do a clustering algorithm, k-means one line in R. I want to do it distributed on massive amounts of data set. I can do it through EMR. Another one is obviously association. If you go to a Family Mart or a Kmart or 7-Eleven, you use that algorithm on a day-to-day basis. You just don't know about it, or better said, they use it against you. What is an association algorithm? Market basket analysis is a very traditional, common one here to find similarities between products. For example, if I buy a bottle of Coca-Cola, I'm very likely to buy a bag of chips, for example, if I have a certain profile. Right, that's a market basket analysis, so bundle products together. Again, those association algorithms, obviously, you know, they're available in R and Spark and Mahout, so they can be powered through EMR at scale. And then lastly, if you want to train neural networks, so neural networks, things like pattern recognitions, for example, like speech recognition, neural network, literally training a brain in a computer, roughly speaking. For those neural networks, sometimes it's useful to use the graphical processor unit of servers, the GPUs, to kind of train neural networks better and do so really fast. If you require that, I want to point you to the fact that for our virtual servers, we have different kind of EC2 instance types. Some of them have more CPU, more memory, and so on, more storage, optimized storage. And we also have specific GPU optimized instances where you can actually tap onto the NVIDIA, we use NVIDIA GPUs, use CUDA language, and run your neural network on those GPUs. Yes, R has integration into it, if that's your question. So you can, you just need to import a certain library, and then you can use CUDA language to tap onto GPUs within R, for example. You want to do that, a GPU optimized DC2 instance might come fairly handy. All right, how about, yeah, question? Yeah. So how many kind of... Right, so how many clustering measures we have? So currently the machine learning, the fully managed machine learning service only touches on classification and linear regression. Right, so clustering currently is not part of it. For classification, it's, yeah? Right, so in terms of clustering algorithms that we see, it depends on the project that you're using. So, right, so it depends on the projects you're using, what clustering algorithms we have. Spark MLit is an example. So Spark MLit, I think you get k-means and KNN and some, you get a bunch of, don't quote me, look at the list and so on. But there's obviously when you run R, you get all the benefits of R, and depending on which library you include in R, that defines which algorithms you have. And then another one on EMR is called Mahout, M-A-H-O-U-T, which has lots of interesting naive Bayes algorithm and things like that. So it depends which project you're using. For the service itself, it doesn't include clustering for now. It only includes classification, and this is binary, so 2 buckets, or multi-class, so multiple buckets, and linear regression. Good question. One last thing that I wanted to discuss is the visualization aspect of it. So obviously we have business intelligence tools and so on. I wanted to demonstrate that some open source tools can come in quite handy. One that I quite like, especially when it comes to log analysis, is called Kibana. So Kibana was a project that was created by a specific person, and then eventually became really popular to a point where a company was founded around it, which is now called Elastic.io. And it's an open source project that allows you to do nice visualization in browser like this by tapping on an indexing engine, which is Elasticsearch, which is an indexing engine, which is based on Apache Lucene, another open source project that has been around for, I think, over 20 years now, nearly. The good news is Elasticsearch can be fully managed and even run on Hadoop so that it can scale, and then Kibana can start visualizing that information quite nicely in browser. Here's just a sample dashboard. You can create your own dashboards and filter things around and click through those dashboards, and we're gonna have a little demo on that in just a bit. Open source, so github.com/elastic/Kibana. This is where you can find it. Now, what I wanted to do is just show you a little demo on how we could put this together. So, So what I figured is, how about we create a little live demo where we actually work on large amounts of data. So one thing that comes to mind is obviously Twitter. So with Twitter, we get, this is a 2013 statistics, by the way, we get about 500 million tweets a day, and an average is about 5,700 tweets per second that we see with Twitter. So how about we put that into an Amazon Kinesis stream, and then from there we pick it up with an Amazon Lambda function so that we can operate on all the individual tweets that are coming into our Kinesis stream. And then I'm going to look for hashtags, and those hashtags I'm going to index them into an Elasticsearch appliance, and that will then allow me to visualize them in browser with the help of Kibana. So let's try this. Right, it's a live demo, so let's see if it works. Just going to test my connectivity. Perfect. So what you see here, before I proceed, this is, by the way, the AWS Management Console. So here you see you get all the kinds of different services that we talked about, like EC2, S3, EMR, machine learning, etc. This is how you can interact with AWS out of the console, apart from the API. So what I'm going to do first is, because we want to feed this into a Kinesis stream, we going to look at Kinesis. So I actually pre-created this. Let's just click on it. I created a Kinesis stream. It's just loading up. There we go. I created a stream which I call Twitter demo stream. So this is my first point of entry. This is where my tweets can come in, and if I click on it, you see it also gives me some statistics around what's going on in that stream right now. You see that right now nothing is in there because I haven't started tapping onto my Twitter feed yet. Now, the next thing that I want to do is, if I use a stream like this, that's great, it ingests my tweets, but what am I going to do next? I want to find the hashtags, so I need to write my own little code. How do I make sure that gets executed upon every event in my Kinesis stream? Well, I use event-based compute, which is, I'll go back here, which is Lambda. So Lambda allows me to run my own code in response to events. And that event is a new item in my Kinesis stream. So what I've done here is I created a Twitter demo Elasticsearch Lambda function. So let's open that one up. And you see this is actually Node.js code. So I could have chosen Java, I chose Node.js here. You can see there's an inline editor. You can also upload it, obviously, as a packaged zip file if you prefer that. What is this piece of code doing? Let's have a look at it. So basically, I get an event which comes from my Kinesis streams. And this Kinesis stream has records. So the records that's streaming into this Kinesis stream. For all of those records, I'm just going to take them out. They're JSONs, because it's a tweet, it's stored in a JSON format. Some cleaning here, they're undefined or whatever. And then I'm going to look for hashtags. So I'm going to find those hashtags and put them in a hashtag variable. I package that back up into a JSON here, add some additional information like date, when that currently happened, extract things like what was the topic that was talked about in the country, etc. And then here I'm going to put it, and you see this is a single server Elasticsearch appliance, I'm going to put it into an Elasticsearch appliance for it to be indexed. How do I do that? Elasticsearch is a RESTful API call, so I just need to use an HTTP call. You see that here. This would be using the Node.js library of HTTP to make that request, and if it was successful, then we indexed the hashtag into the Elasticsearch appliance. So how do we execute this now? Well, we want it to be executed upon every event within Kinesis. How do we do that? Well, we collect that Lambda function to an event source. You see I've already done that here. I'm just going to show you how it would look if I haven't done it. I can click on Add Event Source. And here you find different event source types. So I could say, for example, on a new event within Kinesis, right? And then it allows me to select the stream. It allows me to also tell us the Lambda function in how much batch I want to operate. So I could, for example, say on every event that comes in, that would be batch size 1. That's generally not the best practice, and sometimes you want to do a simple aggregation. So 100, for example, is 1. It fully manages which data it has operated on. It allows you to change things like, I want to trim the horizon, which is a queuing mechanism, work on what hasn't been worked upon yet, or work on the latest one. That's another way of starting it. And then you can enable that event source. We talked about other ones like S3, for example. Can easily connect it to an S3 bucket and say, for example, whenever I have new objects being created in my S3 bucket with a certain prefix, maybe I just want to do that wildcard, then execute that Lambda function, for example. Another one would be SNS or DynamoDB. In this scenario, I'm just going to leave it with Kinesis. So I created that here. I created an event source Kinesis, and I connected it to the Twitter demo stream. So whenever a new tweet comes into Twitter demo stream, this piece of code is being executed to find a hashtag and then eventually put it into an Elasticsearch appliance. Now, before I continue, I'm just going to tell Twitter to actually stream information to my Kinesis stream. I'm just going to use a small little EC2 instance to do that. Now, I don't want to tap onto the entire firehouse, otherwise it's going to be a lot. So what I'm going to do is I'm just going to look for certain words and have them put into my Kinesis stream. So I live in Hong Kong, so what should we listen at? Money would be a good example, I guess. Everybody loves money. What else do we want to listen to? Any cool words? Yes? Dim sum? All right. Let's see if that's popular. Dim sum. All right. So what now happens is Twitter will send this information into my Kinesis stream. All tweets come in. For every incoming tweet, it will call my Lambda function, since my Lambda function is connected to it, and that will index it into an Elasticsearch appliance. Now that Elasticsearch appliance sits here, so I can just load it up. Let me refresh this properly. So this is Kibana. This is the user interface of the visualization tool that sits on top of Elasticsearch. So if I look at Discover, I should see now there are tweets coming in, which is great. A lot about money so far, which is what to be expected. What Kibana allows you to do is to kind of quickly move around in terms of data, start exploring it one by one, and also start filtering it using filter tags on here. It also allows you to create visualization components out of it, like area charts, and line charts, and pie charts, and all kinds of metrics, and then eventually plug them together. So I created a few here. I created some hashtag top 10 lists and pies within Kibana. And that allows you to plug it into a dashboard. And I actually pre-created one, so let's try to load that one up. And here we go. You see so far we're collecting a lot of different tweets, 590 so far, and so far only about money. I'm thinking dim sum too now. I haven't had dinner yet, so that's the next. But this is interesting. You see, for example, now what people are tweeting about. So popular keywords, let's just refresh this, see if it's still working. Yes, it is. Tweets are coming in. We're seeing here money is being tweeted about. Let me change that keyword. I wanna try another competing keyword. So even though I like dim sum a lot, I think not a lot of people are tweeting about it. I have the free Twitter account, so I can only listen to two topics for now. That's why I'm killing it. Let's think about food. I guess that's probably a little bit more popular. So we're also listening to food now. So let's see. There you go. Actually, dim sum was coming in. There was one coming in. Dim sum and food slowly starts comparing. So you see, this is a great way of starting visualizing things. An example of where, for example, I know that people care more about money than food, apparently, since we get more tweets there. And apparently now playing and Game Insight and Money and Android games seem to be very interesting hashtags. And you see, Kibana is an interesting tool because it allows me to drill down in here. I could, for example, say, oh, this is interesting. I want to filter based on this. For example, I want to find all the tags that have Game Insight and food in it, and I apply for it, and there we go, and it filters things out. Or, for example, only food. There you go. Food hashtags like iPhone games, etc. It allows you to work on that data. It allows you to define a time component to it. like the last hour, the last 15 minutes, and it even can do an auto refresh where you say refresh this page every 5 seconds, for example, so that you can put it on a nice screen in the office, and obviously have a live dashboard of what's going on. You see now the refresh is happening, and we see more and more tweets are coming in 2033 already. So money and food, popular topics being discussed about. Now this is an example. Thank you. This is an example of what you can do in a live demo. The key point here is really to think about a few things. The first one is to say, I want to have an environment that is fully managed and goes to any kind of scale, right? If we have a stream like Kinesis, we can do that. We can safely say, give me any kind of input data. Think about the Internet of Things space or scenario, right? Lots of devices out there. Put it somewhere where you can work on it. And then the next thing, instead of like polling it yourself, think about how event-driven compute can help you. Lambda allows you to just say, whenever there's something new, work on it, right? You don't need to manage that aspect. If nothing comes in, you're not even charged for it, right? Because it's execution time that you charged for it. And then you can use that as an ingestion point, and you saw something what I did, right? I only had one virtual server behind it. I don't bother, right? Because I'm the only one looking at this visualization here. Data would still be nicely stored through my Kinesis stream, right? So you can think about different stages, Elasticsearch and Kibana being a nice way of using open source tool to live visualize this. Now, obviously for your specific use cases, you might decide, I want to also store it in an S3 bucket. I might want to load it into my Hadoop cluster, into my R environment, etc., and work on it. By the way, R has also integration into Kinesis if you want to work directly on a stream. Now, this is all I had for today in terms of topics. I want to cover off a few questions and ideas you have. Before I do that, Lenny, my colleague, gave you a little feedback form earlier. I think you have a little piece of sheet paper in front of your lab. If you haven't, you get some more copies there. It's always great for us to kind of get a feedback of how you like the session, but more importantly, if you fill this out, you get 50 US dollars. This is not Taiwan dollars, it's US dollars. You get 50 US dollars credits in our platform, so you can start using some of those services. This Twitter demo that I just presented, for example, would cost you roughly about 20 cents an hour. So you could let it run for a fair amount of time with 50 US dollars. Apart from that, I went through a bunch of different services, and you see we get lots of different services. If you have something that you're interested in building, talk to us, because we can help you identify what you should be looking at. Don't go out and use all the services. I don't know any customer who uses all of them. So look at that. Another thing, I'm here in Taiwan, obviously, to come to this lovely user group, but also some other cool events with III that we organize. If you got time, this Wednesday, we actually organize an event on explaining with how to scale applications on top of AWS. Little disclaimer, it's me partially talking, that piece is in English, even though this is written in Chinese. The later workshops are going to be also with my Chinese colleagues, where we get hands-on on your laptop to actually try things out. So if you get time, sign up for it. There's the URL here. This Wednesday, it's a full day. It's a presentation style in the morning, and then hands-on keyboard. You bring your own laptop and you can try things out live together with us in the afternoon. It's going to be at another CLBC building. Here's the address. I can only read type A. You can help me with the rest. So if you want to attend that, sign up for it. And apart from that, I want to thank you very much for your attention and want to open the door for questions. Thank you. Yeah.
Just demo the example. So is there any code I should write, for example,
For this specific example, if you would like to do the same example, if you would need to write code. So the only piece of code you would need is the one I showed, which is to find the hashtags. right? So that piece, I can share it with you. Don't use it in production. I haven't tested it really too roughly. But happily sharing that with you. Apart from that, we also got code samples in the AWS Labs part, so GitHub/AWS Labs. There are lots of code samples there too, which is a good way to kind of get started with it. Yeah.
Another question is you just mentioned the database, Redshift.
Yeah.
It's a current database. And should I use a specific library to use the database?
Very good question. So if we use a columnar database like Amazon Redshift, for example, do we need a specific library to talk to it? The answer would be no. You only need a SQL, so it's fully ANSI SQL compatible. So your ODBC, JDBC connector could be used in the scenario of R. You can just write your normal SQL queries. There are a few limitations of some very specific aggregation statements that you might or might not be able to do. What I would say is you find pretty much compatibility with a PostgreSQL-like kind of database environment, because that's where we spun it off from the initial fork. That's what you'll find it. For most queries, no specific requirements. So just normal SQL query, just ODBC or JDBC is the way you talk to it, and then you throw your query against it. Good questions. Yeah?
Because I'm quite new to this ecosystem, but I'm curious, does you regard like Apache Kafka as a competitor compared to Kinesis?
Yeah, it's a very good question. So the question is if Kafka would be a competitor to Kinesis, and I wouldn't necessarily say it's a competitor. The way we see things is when we come up with services like this, it's not that we're trying to build something new, but it's to help our users on making their life a little bit easier for us. So could you build this with Kafka? Absolutely. And would I use Kafka if I would build a demo like this if I wouldn't have Kinesis? I probably would. What Kinesis does for you is that you don't need to worry about managing a Kafka stream. What it would mean if you run your own Kafka, you would need to run multiple servers, at least 2, to make sure that it's highly available, and then you would need to scale them out. Overall, unless you do a fairly good job in utilization calculation, it's probably cheaper to use Kinesis than running Kafka on EC2, because EC2 you're not charged on throughput, but it would be on on the per instance kind of hour charge, and you would need to figure out the rest and how to scale it. While something like Kinesis is per transactions per second kind of charge, where you say 1,000 TPS, that's what I pay. Full stop, right? 2,000 TPS, this is what I pay. If I need more, I just adjust it, and I get that part. So achieves probably the same thing, but with Kafka you would need to manage it yourself. If you don't want to do that, then something like Kinesis is interesting.
I have another question about GPU servers, because when you provide those GPU servers, if I just launch like 2 or 3 instances, do I have to manage the parallel data by myself, or I can just treat it as I have like 16 GPU, or I have to manage the data by myself?
So the question is if we have multiple GPU instances, if we could have a common data layer in between. So from our perspective, there's no restriction in doing that. You would just need to have a file system that would allow you to do that. One way of doing that would be using something like an HDFS or Gluster FS that distributes the file system across the GPUs. Another way would be using a clustering software that potentially has integration to it. Depends on your use case. When it just comes to storage, so if it's simulation and it's heavy on the GPU but not heavy on the data, it's probably easiest to use a distributed file system and then use multiple of those. We get different sizes of GPU instances too. So if you say I just need a bigger one, you can also resize those instances on the fly. So you just say shut down, give me a bigger one with more GPUs, bring it back up, do my simulation and shut it down again. Those are also elements that you could do. So I would probably in that scenario I would look at why do I need multiple GPUs? Is it to get more performance? Could I achieve the same thing by scaling the individual instance up? If not, well then, is it only storage that I have distributed? Then potentially just Gluster FS, HDFS will do. Otherwise, maybe something like Spark can even be interesting. If you say, I want to have a distributed in-memory cluster, but tap onto the GPU for certain computation, you could also achieve that through it. Obviously, you need to write the CUDA language in Spark, but yes, you could. Good questions. So. Any other questions for today?
Question about GPU supported for the TSOs. How do performance compared to the CPU or GPU? Because I heard that the simulation by software is not really common.
Yeah, so in terms of the question, what's the difference between the CPU and GPU performance? It's a tricky one. So the way you can see it is GPUs are really good at doing certain operations. And you'll find that if you use a GPU, like an EC2 GPU, you need to use CUDA language, which is an NVIDIA chipset-specific language, and that allows you to do certain operations. If you can do those operations, you'll find a huge performance increase here, because a GPU, like the smallest one that we offer, I think has 1,500 something cores, right? Comparing that to most virtual servers that potentially only have like 2 cores, maybe 16 cores. Here you tap onto thousands of cores. The larger ones, they have over 8,000 different cores, I think more than that even. So you suddenly have all those cores that you can use, but only for operations that are supported by that language, right? So if those operations are supported, and for like neural networks, that's a good pattern here, some certain simulations, then you get a much better performance boost on the GPU. But you can't kind of fully compare, because a CPU has so many operations that it can do. GPU is limited to only a few. Those are very useful for certain use cases, like rendering, which is what the GPU was designed for, but another one is machine learning algorithms to do simulations, for example. And here the benefit is you get thousands of more cores instead of the normal CPU to parallelize that operation. Yeah. Good question. Great.
请问还有问题吗？OK， 那因为其实刚刚一开始的时候我们也介绍一下，那个 Oliver 他目前的话是那个 AWS 的 Specialist， Machine Learning 的 Specialist。那他目前非常忙碌，因为尤其是在10月初的时候，他即将去美国拉斯维加斯那边会有一个 Reinvent 的活动。那他们在百忙之中，现在还愿意到我们社群分享一个这样的议程，我是非常感动，非常感谢他。所以我们最后还可以先跟他鼓励一下，谢谢那个 Oliver。
And please feel free to, like, if you have any ideas or feedback, something you want to hear about in terms of AWS and R or anything specific, post it to the meetup group, send it to me, or send it to Noah. I'm happily, coming back, talk about something you really want to hear about. This was just an overview, but feel free to just drop me your questions or ideas you want to have. Happily addressing that. Thanks. Thanks.
Hi,